Hello, and welcome to Comprehensive Rocket Science. My name is Rob Roundtree. So today we're going to be going over Starship, and not just Starship, but specifically, can Starship deliver 100 tons to orbit, and how can it do that? So what we're going to do is we're going to go over some basic rocket science principles and back them up with math and integration. I'm going to show you all the calculations, and we're going to figure out, can Starship deliver 100 tons to orbit? If so, what altitude can it reach? And if not, how much can it lift into a reasonable orbit? So let's get right to it. All right, first of all, for those who don't know, Starship is SpaceX's next generation launch vehicle. Starship is designed to be fully reusable, fully and rapidly reusable. It has an advertised 100 to 150 tons of payload to low Earth orbit. It is expected to have in-orbit refueling once completed. And it's currently in development in Boca Chica, Texas. It's SpaceX's Starship facility there. It has several test flights under its belt, low altitude test flights up to about 10 kilometers, 10 to 12 kilometers, which is roughly 33,000 feet. And all those have had varying levels of success. They've always successfully ascended, and then they've had a couple issues on the landing, but finally stuck the landing in their last flight, which was this past summer. Since then, we haven't seen anything. SpaceX has been gearing up for a orbital test flight, which we expect will be coming in January or February of this next year. So the big thing about Starship, right, is it's fully and rapidly reusable. Starship is made of stainless steel, which makes it inherently heavier. So there are some concerns about its capability. It's being advertised as delivering 100 tons to low Earth orbit, but we don't know too much about those assumptions. What assumptions are going into that, right? Clearly, the math is good enough for NASA to be happy with it. Obviously, SpaceX is happy with it. They're doing their best to make improvements, but there could be some underlying assumptions that might be a little overly optimistic, especially knowing SpaceX. They tend to have optimistic expectations for themselves, not without reason, because they were able to really refine the Falcon 9 launch vehicle and make it way more capable than it ever was advertised to be initially. So it's very possible they could do the same thing with Starship. However, they have a long road with Starship. They've promised a lot, and they're working to make it all happen, but we'll see if it happens. That being said, the first piece of Starship is 100 tons to low Earth orbit, which is a concern for a vehicle. That'll be the most any launch vehicle has been able to deliver to orbit since the Saturn V, and it's a big deal for a vehicle that's stainless steel, which is one of the heavier things you can build a rocket out of, and which we haven't actually seen fly yet. So I figured, let's take this moment. Let's see what Starship has right now in terms of engine, specific impulse, mass flow. Work with the Raptor 1, the current engine version, and look at some calculations to determine whether the vehicle can actually deliver 100 tons to low Earth orbit, and see how high of an orbit it can get to, and what sort of speeds we're looking at, all that kind of thing. So I'm super excited about it. We'll get started here. The spreadsheet we're going to be looking at is a work in progress. This video is really just sort of an interim update on my progress so far in calculating a Starship trajectory. It has the publicly available numbers, right, for the Raptor 1, as well as using the 29 engine configuration of the booster and the 6 engine 3 vacuum 3 sea level engine version of the Starship itself. So these numbers will change in the future. When we actually see changes to the vehicle, I'll post an update, which will hopefully have a more updated version of the spreadsheet, something a little more professional, maybe a paper to go along with it. And I'll have the spreadsheet totally updated for all the new numbers. All right, let's dig right into it. So starting out in these calculations, I had to make basic assumptions about Starship itself, to include both the Super Heavy booster and the ship. And you'll see these assumptions here. So we'll go through these assumptions. We'll talk about some of the initial calculations I did, and then we'll go through the trajectory modeling, where I actually integrate over time all these different values and try to calculate a trajectory for Starship. All right, so first off, the total system weight we're estimating at 5,215 tons. This is just a sum of the Starship weight and the super heavy weight and the booster weight. Nothing too special to see there. So ISP, that's specific impulse, which is a measure of basically the efficiency of the engine. So if we look at some basic functions for just calculations in rocket science and propulsion in particular, you have a couple things that stand out. So there's specific impulse, which is the impulse per unit weight, and there's total impulse. So total impulse, we'll start with that just because it's a little simpler or more intuitive. Total impulse is the amount of force that is delivered to the vehicle over time. So total impulse can be thought of as, so we'll say IT equals the integral of force over time. And that's obviously from 0 to t. Now, the higher total impulse, the more force is delivered to the rocket. That's pretty simple, right? All right, so total impulse, as described, is the force that is delivered to the rocket over a certain amount of time is total impulse. So the more force is delivered to the rocket, obviously the further the rocket goes, depending on rocket weight. So where you take, specific impulse, of course, you can think of as like efficiency, basically, which is, how much force you get out of an engine for the amount of fuel that's burned. And where you get this is so specific impulse is going to be equal to the integral of force dt over your constant gravity times the integral of mass flow dt. And this is so what you're basically saying here is, okay, how much total impulse is applied to the vehicle, aka, what's the sum of all the forces applied to the vehicle, and then what's the sum of mass flows, aka what's the sum of all the propellant consumed. And this gravity constant just changes it from mass to weight, so you end up with better units. So the more force you can deliver with a lower mass flow, the more efficient your engine is. And this is pretty straightforward. Initially, if you think about it as like a car with gasoline, you're able to deliver a specific amount of force over time, right, with a certain amount of gasoline. This is a little bit different for rockets. When you think of, a rocket could be fueled with hydrogen and oxygen, it could be fueled with methane and oxygen, or it could be fueled with RP1, which is a heavy kerosene basically, and oxygen. So the weights of these fuels are considerably different from one another, which means that hydrogen will sort of naturally have a much higher specific impulse compared to methane, which has, again, higher than RP1. So you'll see hydrogen engines will always have the highest specific impulse. This is traded though because they're less dense propellants, hydrogen and methane, so the fuel tanks will be bigger. So if you think of the fuel tanks of a rocket, your hydrogen tank is going to be much larger than your methane tank or your RP1 tank for the same weight of propellant. Now hydrogen is more efficient, but it's a trade-off you have to make, because remember, these fuel tanks are filled with, these fuel tanks are mass in themselves, and obviously reducing the inert mass of your rocket as much as possible is better. So having a heavier fuel tank is not always good. So moving on from specific impulse. All right, the next thing we have is thrust. Thrust I've here measured in tons, and that's just Elon typically measures thrust in tons. A lot of the published figures you see are in tons, and then that just makes the math easy. You can sort of get rid of your gravity constant often if you measure thrust in tons. So we're saying thrust of the Sea Level Raptor is 185 tons. Weight of the Sea Level Raptor is 1.8 tons per Raptor. We've got 33 engines. That's going to give us a total thrust of 6,105 tons. And a lift-off thrust-to-weight ratio of about 1.17. Now you can see, this is considerably lower than Elon, I believe, asserted that the vehicle would have a thrust-weight ratio of about 1.5 on liftoff. However, he, is likely using different versions of the Raptor engine that he expects will have higher thrust. So the mass flow, we need mass flow in order to be able to do some of our calculations, specifically how long the vehicle is going to burn. So mass flow we can actually calculate, and I'll show you how to do that. So mass flow can be calculated using specific impulse and total thrust. What we actually do here is for specific impulse, because we don't have the total impulse integral or the mass flow or gravity, and we're actually able to use SpaceX published numbers of specific impulse for the sea level Raptor engine, specifically the Raptor 1. So that's where we get this 330 seconds number. That's a published number. From that, we can calculate the mass flow, which allows us to calculate burn time. So to calculate mass flow from specific impulse, you can see it. The integral is right here. So it's going to be really derived from that. So you can say that your specific impulse, if you assume negligible start and stop transients for both your thrust and your mass flow, and you also assume that force and mass flow are both constant over time, you can pull them out of the integral and just say that force times time over gravity times mass flow times time equals specific impulse. Cancel out the times. You're left with force over gravity times mass flow equals specific impulse. And then if you do a quick units calculation here, you'll see you have newtons on the top, which is kilogram meters per second squared. You have meters per second squared times kilograms per second on the bottom, which gives you, meters per second squared over meters per second cubed, and the seconds just comes to the top and turns into seconds, which is your unit for specific impulse. So from that mass flow, you can easily calculate burn time. That's obviously just going to be your mass flow divided by the total amount of fuel and oxygen in the tanks divided by your mass flow. So for the first stage of the Starship, we have a burn time of 194.5 seconds. We'll reduce that to less than 194 for our purposes, because we do have to consider the fact that the booster is going to re-enter and need some amount of fuel for its re-entry burn. It's not performing a re-entry burn, but for a boost back burn followed by a landing burn. C, effective exhaust velocity, that's just calculated from mass flow and total thrust. It's not used really for this exercise, so I won't belabor it. Oxygen and methane amounts in the tanks. Here we had to basically guess based on what we knew about the vehicle. So we knew that the vehicle would have a dry mass of 200 tons. Elon said he wanted the vehicle dry mass to be at or below 200 tons, so there you have it, 199.4 tons. We also know the wet mass of the vehicle is 3,400 tons. So from that, we're able to come up with the oxygen and methane amounts using the ratio that they plan to burn oxygen to methane at, which is 3.6 roughly. So that's how we get those numbers. All right, and then you can see here, dry mass without engines, with engines. Total wet mass of the first stage is 3,800 tons, and then a dry mass to wet mass ratio. All right, moving down to the ship. So Starship itself, you'll see the sea level Raptor and the vacuum Raptor numbers. So one important thing to note, for both the booster and for the ship, we're using 330 seconds of ISP for the sea level Raptors. Now, as I understand it, that is the specific impulse of the Raptor at sea level. And the performance of the engine is going to increase as you increase in altitude. Even for an engine that's optimized at sea level, basically you'll have this chart where your performance Basically, say you have, like a point of 100% performance here. If your engine is optimized for performance at sea level, say this is sea level, this is, I don't know, 100 kilometers, which is near vacuum, right? If your engine is optimized for performance at sea level, it'll have 100% performance at sea level, and then by the time you get to 100 kilometers, it has maybe 105% performance. Now, most engines are not optimized for sea level. Most engines are optimized for around 40 kilometers. So, say this is the ideal expansion point at 40 kilometers. So you'll have a graph for an engine that's optimized for 40 kilometers. Your graph may look more like that, where you'll have relatively lower performance. Say it's performing at 95% here at sea level. It'll be performing higher, say 105% at 40 kilometers, which is ideal expansion at 40 kilometers, and then it'll continue going up. And basically that's just the optimization for your ideal expansion ratio. It tends to be about 40 kilometers for first stages, but that's something we'll cover in much more depth later, and I need to do some research on that. Now, that is just for the sea level Raptors. Obviously, for the vacuum Raptors, we know they're optimized for vacuum, and the specific impulse number that's given is for vacuum. But basically, the point of showing you this graph is that these ISP numbers for the booster and the sea level engines on the ship are reflective of the ISP at sea level, so we do expect engine performance to increase as we increase in altitude. All right, so same thing, thrust 185 tons on the sea level engines, weight 1.8 tons. We'll say there's 3 of them, and then there's your expansion ratio. All right, for the vacuum Raptors, ISP has been given as 378 seconds. Thrust is the same. It'll likely be higher. That should probably be higher. Weight, we've estimated at 3 tons, the number of 3 tons. Expansion ratio has been advertised as 80. Tank weights, again, we basically use the burn ratio of 3.6 to 1 for oxygen to methane. So Starship uses a oxygen to methane burn ratio of approximately 3.6 to 1. That's a mass of oxygen to max of methane. The stoichiometric ratio for oxygen to methane is 3.7 to 1. Starship is going to run higher on methane, so relatively less oxygen per mass of methane, in order to have lower combustion temperatures, and that's just going to help improve life on the engine and avoid any temperature issues within the combustion chamber. Basically, we got these numbers again because we knew the total weight of the vehicle wet and dry, and we're able to figure out how much propellant it had. So there we got the dry mass with no engines, dry mass with engines. We're assuming a 100-ton payload, so remember that's inert mass that won't do us any good, similar to the dry mass. And then our total wet mass of 16 tons or so, with a total thrust from your 6 engines at coming in at 1,110 tons. 1,110 tons. So it is worth noting here that your initial thrust to weight ratio of the of Starship is going to be 0.78. So with a thrust to weight ratio less than 1, you're looking at more than likely flying Starship on a lofted trajectory. So this is often done to the Atlas V with the Centaur upper stage does this as well, where basically this is your you have Y and X here, right? And the vehicle gets launched. Your first stage is actually going to launch it higher than it needs to go. You're going to perform second engine start. You're going to continue. And then as the vehicle travels, as it's pushing, it's actually going to have to decrease in altitude. So your first stage is going to push it up higher than it needs to go. It'll keep going up as it gets going, then it'll actually decrease in altitude, and they want second engine burnout to occur, or second engine stop to occur at the orbital insertion altitude desired. This is called a lofted trajectory, and it happens if you have an underpowered upper stage. Specifically an upper stage with a thrust-to-weight ratio less than 1, definitely underpowered, and you need to fly that vehicle into a lofted trajectory because you're not going to be able to get the velocity you need before you start going down, basically. All right, so mass flow we've estimated for the Starship using ISP and total thrust. You can see that there. That was the equation we presented up here to get mass flow from specific impulse, and then burn time from that mass flow. Long burn time, 381 seconds. Quite a long burn time, and so having that long of a burn time and this low of a thrust-to-weight ratio, like I said, is going to put you on that lofted trajectory. And it's really going to increase your gravity losses. Now, this is something you'll see done with very efficient upper stages, such as the Atlas Centaur. The Centaur upper stage, very efficient. It's hydrogen. It's it's a great vehicle. But the launch vehicle or the first stage does have to loft the second stage in order to eke out that performance. Starship, on the other hand, heavier. I wouldn't, obviously it is still relatively high performance compared to Keralox, but still not Centaur levels of efficiency. Whether it's worth lofting it or not is something that SpaceX it sounds like is still figuring out. If you follow Starship, you know that they recently increased the number of vacuum engines to 6 as opposed to 3 for a total of 9 engines altogether. That's going to significantly increase the total thrust, and likely, I'm expecting, is going to increase that thrust-to-weight ratio to make it 1 or more, close to 1 at least, so that you will have a lower burn time, obviously, but you're going to have higher accelerations, and that's going to allow you to not be on a lofted trajectory and not have so many losses due to gravity. I was just editing this and wanted to make a point of clarification because I don't want people to think that having a second stage initial thrust-to-weight ratio of 1.0 is the criteria for whether or not the first stage has to launch the second stage into a lofted trajectory. So a lofted trajectory, all that means is that the first stage pushes the second stage up higher than it needs to go, and as the second stage travels, as it gains velocity in the x direction, it starts to reduce in altitude due to gravity weighing on it more than its y component of thrust. So to avoid being in a lofted trajectory, you have a couple options. Really, it generally involves having a higher thrust to weight second stage, but there are a couple different options there. But really, all it means is that you're at orbital speed, so your orbital insertion speed, where your x velocity is all you need to make a full orbit around the Earth, and just fall around the Earth basically. So you reach that orbital speed in the x direction prior to losing altitude in the y direction due to the effects of gravity being greater than either your initial push from the first stage or any y direction that your second stage provides, any y velocity, I should say, that your second stage provides. All right, so those are all our assumptions for Starship. Let me know if any of these numbers look incorrect, if you think anything needs to be updated, anything like that. And on the next tab, we're going to go into how all these numbers come together to give us some of our initial estimates for payload to low Earth orbit. All right, so now that we've covered some basic parameters for the Starship vehicle, let's talk about our goal. So the goal of the vehicle obviously is going to be to get into orbit. Let's say we want to get in a 150 kilometer orbit, which I understand is quite low, but that will at least suffice to be in space, at least for a couple orbits before drag pulls us out of the sky. Now, you can calculate the circular orbit velocity required to get into a 150 kilometer orbit fairly easily. You can see I've done the calculations here in Excel. And I've also done them in my Introduction to Orbits video, so if you haven't seen that, take a look at it. So here to calculate the circular orbit velocity, I'm just taking the square root of the gravitational parameter, μe, divided by our distance from the center of the Earth, which is the sum of the Earth's radius, plus our altitude in kilometers. And that number is going to get me the velocity required, in this case in kilometers per second, to orbit the Earth. And you'll see for a 150 kilometer orbit that comes out to 7.81 kilometers per second. So here you can see I talk about a 28.5 degree inclination orbit. That will come to play in a second when we talk about calculating the launch vector. And this note about only working for prograde orbits, that only applies to this spreadsheet that I developed. This orbit inclination can be retrograde as well, obviously. All right. So for the launch vector, it ends up getting quite complicated. Basically, what we come to find is we are going to be will really be ascending or descending node, doesn't really matter, because we're going to be launching at 90 degrees. So launching at 90 degrees is going to cause our inclination to be 28.5 degrees. So the lowest inclination you can get from any particular launch site is going to be the inclination of that launch site itself. So Kennedy Space Center, which has a 28.5 degree inclination, the lowest inclination we can get, that is if we fly straight east upon launch, it's going to be a 28.5 degree inclination. Now we also know that Kennedy Space Center has a 408.738 meter per second eastern velocity, and that's due to the rotation of the Earth, right? So the Earth rotating does impart some velocity to launch vehicles upon launch, and that comes into play in calculating how much delta V you need to reach orbit. So in fact, if we're able to deliver, see here we need 7.81 kilometers per second. Well, if we have our 400 meters per second that the Earth is helping push us, really we just need to deliver 7.41-ish, or 40 something-ish kilometers per second of delta V to the launch vehicle in order to get into orbit. And that's after we take into account, of course, any losses. Now our losses are primarily going to be due to gravity, drag, propulsion losses, steering losses, these kinds of things. I am not going to belabor losses too much in this video. I will do that at a later time. However, right now I really just want to talk about we'll talk over sort of how those losses occur, but I really want to focus on the integration method. We're actually going to integrate all forces over time, so the losses are going to just naturally sort of come from those calculations, but we won't be calculating losses specifically. All right, so here basically what we're calculating is for a V burnout of 7.81 kilometers per second, we have a 408 meter per second eastern launch velocity, or launch site velocity, so we need 7.409 kilometers per second of delta V in order to insert into this 150 kilometer circular orbit with a 28 degree inclination. So what we're briefly going to cover gravity losses and aerodynamic losses. Steering losses are going to come into play because we will not assume that the vehicle waterline marker, the vehicle thrust vector is always aligned with the velocity vector. So those will sort of naturally be taken into account. Steering losses. Propulsion losses we also aren't going to consider because here you see we've estimated the sea level specific impulse and the sea level thrust of the sea level Raptors. We expect those numbers only to improve as the rocket increases in altitude. So we don't expect any propulsion losses. Now, this would be different if I had been using either the ideal expansion ratio, ISP numbers, and thrust numbers for the sea level Raptor engines, which, like I said, are probably having probably have an optimum expansion ratio around a 40 kilometer altitude. Or, this would also come into play if I used vacuum numbers for ISP and thrust for the sea level Raptors. However, because I'm using the sea level numbers, those are already basically the worst it's going to get. So I expect it only to get better, so I don't expect propulsion losses in this case. All right. So for gravity losses, basically gravity losses are going to be the integral of g sine gamma dt. Basically, you're calculating how much gravity affects the trajectory of the rocket. There are several empirical methods to do it, which are explored in some detail in a book that I have a copy of. And that book I'm referring to is Design of Rockets and Space Launch Vehicles by Don Edberg and Willie Costa. Quite a good book for talking about launch vehicles, losses, that kind of thing. All right, so gravity losses, briefly talked about aerodynamic drag losses. Yes, we are expecting aerodynamic losses. Again, they're going to fall out in our calculations because we'll be calculating aerodynamic force and integrating that over time. This integration, actually integral dt over mt, and will actually perform. Well, we're not doing that one specifically, but because that relates to delta v, we're actually just going to going to integrate drag over time, basically. And you'll see what I do. I basically use an Excel spreadsheet, integrate and sample every second to integrate over the flight of the vehicle. Here it estimates a delta V loss of 10.3 meters per second. Seems kind of low. I haven't done the calculations yet on my spreadsheet to see what portion of losses it accounts for as being drag losses. But it is worth noting here that your losses on larger vehicles are typically smaller than your losses on small vehicles, and that's because your delta V has to be divided by your mass there, and because of the square cube relation, your surface area will increase by your radius of your launch vehicle squared, whereas your mass will increase by the radius of your launch vehicle cubed. So you definitely have some gains from a drag perspective for a larger vehicle. All right, let's get into the trajectory modeling. So here you can see basically what I've tried to do is take the forces that are on the launch vehicle at any given moment in time and integrate those for the entire flight of the vehicle. I start at 0 seconds and go all the way to burnout of the first stage at 184 seconds. I have a 3-second period of 0 thrust during stage separation. Start the second stage at 188 seconds of total flight time, 0 seconds of 0 seconds of second stage flight time, and then continue on with second stage until it's burnout at 383 seconds of second stage burn time, 571 seconds into flight. And we'll talk about the results a little bit in a minute. So just sort of going through these columns one by one. First of all, I guess some clarifying assumptions about this method, right? It does assume 0 angle of attack. Now that doesn't mean that your steering losses are 0, because your gamma, you still have a gamma, a flight path angle, which is the difference between your thrust vector and your velocity vector. So I do have a gamma. However, I don't have an angle of attack. There's no relationship for increasing your drag reference number for angle of attack or anything like that. I just use a constant drag reference number, so that's worth noting. And then, any additional steering losses due to angle of attack in addition to gamma would not be accounted for. We're basically just assuming that the vehicle flies with 0 angle of attack for the entirety of flight. Second assumption assumes standard day. There's a great deal of depth you can go into in talking about what standard day means. I'll touch on some of it and how I derive the formulas here, but suffice to say, we're talking, I think it's 59 degrees, maybe 51 degrees Fahrenheit. I think it's 15 C, and standard atmospheric density, standard atmospheric pressure, that kind of thing. Another thing that is worth noting, is that it assumes the curvature of the Earth is negligible. Now that doesn't tend to be a problem in most launch vehicle cases. However, here, we've got a second stage that's burning for 370 seconds with a fairly low thrust to weight ratio. That's getting lofted. So your downrange travel ends up being significant, over 1,000 kilometers by the time you have second stage burnout. Now, so to say that the curvature of the Earth doesn't matter much is correct, but it will make a difference. For instance, here at a downrange distance of 1,300 kilometers, the internal angle. So, for instance, here, at say 1,400 kilometers downrange, your downrange internal angle in radians is 0.22 radians, and that ends up being 12.6 degrees. So being 12.6 degrees, we can do the calculations right now. So we know that say what's our burnout downrange distance? All right, 1497. So 1,500 kilometers is our downrange distance. So we've got the Earth. Oh God, that's terrible. All right, let's try that again. So we've got the Earth. We've got our vehicle. We're traveling downrange. So as we travel downrange, we're really traveling like that. Whatever. Now we know that our downrange distance when we're done is 1,500 kilometers. So what I've calculated here is that 1,500 kilometers ends up being a internal angle of about 0.22 radians. So what we do is here we say, this angle, we'll call it theta, our downrange internal angle is 0.22 radians. Now, in order to find out, the change in altitude over that time, you can simply take. So we have our r here, right? This is h and this is r as well. But it's difficult to to change your trajectory to go from r to r plus h. So we're going to assume we're at r the whole time, big R. So you've got r here. R is equal to 6,378 kilometers. That's the radius of the Earth. We know that the internal angle is 0.22 radians. So basically, we have, this is r, that's r. The difference, this is just a right triangle, right? So this distance right here is what we're looking for, right? So that distance is going to be r minus r cos theta. R minus r cos theta equals delta h. And then, we know r is 6378, times 1 minus cos theta. And then just doing a quick calculation, so you assume you get about 153 kilometers from that delta H, which is significant. That being said, I don't go into it in detail here because I'm not sure that all the other variables are accounted for, so I'm just going to neglect H. In this case, my next video will include corrections for H, as well as a couple other things. Moving along through the spreadsheet, we've got gamma. So the way we're modeling the trajectories, we're actually going to be changing gamma. So initially, we'll be using gamma equal to 90. We say we tip over at about 35 seconds. And these are, gamma basically is the only thing that changes through this whole spreadsheet. So, and the reason I did that is because I wanted to say that we're changing our rocket's direction in the direction that it propels itself, that it exerts thrust in order to change our trajectory. I modeled this. I tried to do optimization, haven't gotten it to work yet, but I've been through this a lot, trying to get different numbers and sort of hone in on an optimum trajectory. This is as close as I've gotten right now, but basically we'll tip over at 34 degrees, go from a gamma of 90 to a gamma of 89. From there, we're in a gravity turn, I believe. I think we are on a gravity turn from there, in which basically you have your gamma dot, which is the change in gamma caused by gravity. You can see it right here. It's pretty complicated. I'm not going to go into it in depth, but there is a Wikipedia page that we can bring up on a different talk to discuss how a gravity turn works. But basically, we'll be in a gravity turn for the entirety of the first stage burn, I believe. Yep, the first stage burn ends at a gamma of 29 degrees. Remember, zero angle of attack here the whole time, so your gamma angle is actually the direction that the vehicle is pointed. So here, where 90 is up, 29 degrees is obviously mostly horizontal. We have 3 seconds of no thrust, second stage relights at 28.14 degrees gamma, and then it holds a constant 28 degrees gamma for the rest of the flight. And that is going to, now as you fly, of course, the vehicle will start decreasing in altitude, right? And that's what we mean by a lofted trajectory, where the first stage takes it, say to here or so. First stage, pops off. Second stage keeps going. Now the second stage, the trajectory is going to look something like that, right? But the whole time, you're here, the vehicle's still pointed up, trying to get you leveled off. Basically, because it has such a low thrust to weight ratio, and it's not pointed straight up, that you're not able to compensate for gravity until basically burnout is what the optimum case you would, or burnout or second stage engine stop is where you would bottom out. So that way you're just that would be like injection into your periapsis or your apoapsis, where you'd have a zero flight path angle at that point. All right, so there's gamma dot. That's the change in gamma that would be due to that would come from a gravity turn. Like I said, I use a gravity turn after 34 seconds in the first stage burn, but I don't use it after that. Your angle of attack. I do list angle of attack here. It's just not used in any of the calculations. But you can see that your angle of attack, maxes out at over 30 degrees here. You have a negative 30 degree angle of attack. And I believe it should be a positive 30 degree angle of attack, where this is your case. The vehicle is pointed 30 degrees higher than the velocity vector. So it is worth noting that you have quite high angle of attack here at approximately 266 seconds in a second stage burn, as when the maximum is. That being said, though, your altitude at the time is 141,000 meters, so the atmosphere is negligible at that point, and you don't expect any problems with that large of an angle of attack due to either gravity or aerodynamic instability. Shouldn't be a problem when you're that high up. All right, x velocity and y velocity. So here, x is aligned with the local horizontal, y is the local vertical. That's important to note, because as the Earth curves, x and y could change. But here we're saying x is down, y is to the side. H is your altitude in meters. Here's your downrange distance in meters, your downrange internal angle, which we already discussed how we calculated. The downrange internal angle, well, actually, we didn't talk about how we calculated that, but that's pretty simple geometry. Theta is equal to S over R, where S is your distance, and R is your radius of the Earth. Theta is going to be your angle in radians. That's how we calculate the internal angle. S, of course, is going to be calculated just using your velocity, specifically your x velocity. All right, vehicle weight. That's just taking the mass and performing some constant calculations, multiplying by 1,000 to get kilograms, and then multiplying by gravity. Vehicle mass. That's going to start at the parameters we discussed in the beginning of this video, and it's going to decrease by your mass flow every second. Your mass flow, of course, is that value we discussed when we talked about the ship parameters. Thrust is going to be constant parameter. And, obviously these things are going to change when you go from the booster to the ship, right? So the booster thrust is much higher on the booster than it is on the ship. Mass flow is much higher on the booster than it is on the ship, etc. Thrust to weight ratio, simply, it's like thrust divided by weight, obviously, thrust to weight ratio. So here we divide X and Y thrust into components, and those components are determined by gamma, I believe. Yep. So again, gamma is your waterline angle, so your thrust is pointed in the direction of gamma. Again, Y thrust here determined by gamma. So total drag. I actually have a lot to say about drag, unfortunately. Basically, total drag obviously is just the root sum square of your X and your Y drag. X drag is determined by your X velocity. Y drag determined by your Y velocity. Otherwise, they are identical. We've got your coefficient of drag, atmospheric density, air temperature, speed, Mach number will all come into effect talking about drag. All right, let's talk about drag. So, unfortunately, this is a pretty complicated topic. Now, I'm going to go over some equations. They are, mostly I got them from that same launch vehicle textbook. However, they're very common drag equations that you'll see anywhere for aerodynamics. And, for planes, it's basically the same as space vehicles, with the exception that there may be some things you can assume are constant, or you may be able to neglect in the case of aircraft that you can't neglect for launch vehicles. But we'll go through all that. Other resources for this I found were just some places where you can find the temperature, sort of the standard atmosphere, right? The temperature of the atmosphere as you increase in altitude, all the way from the troposphere to the mesosphere, and then also websites that talk about the atmospheric density and how that changes over time. I went into quite a lot of depth modeling this, so we can talk about it. Okay, so we're going to start this process talking about the drag equation. So the drag equation, like I said, same for aircraft as it is for rockets. Basically, D, that's your force of drag, is going to be equal to CD 1/2 rho v squared. Sorry if my rho is a little weird. S ref. Those of you who have seen this kind of stuff before, you'll recognize the coefficient of drag. 1/2 rho v squared is your Q dynamic pressure. That's little q. And then S ref is the reference area of your vehicle. So coefficient of drag, that's a number basically telling you, depending on your Mach number and the shape of your vehicle, it's a constant telling you how much drag to expect based on those two things. 1/2 rho v squared, that's just going to be your dynamic pressure, Q. Have you ever heard of max Q? This is what people are talking about. So max Q is the point of maximum aerodynamic pressure on your vehicle. And then, but it's dependent on rho, which is your atmospheric density, in kilograms per meters cubed, and then V, which is obviously your vehicle velocity in meters per second. And V, if I change this to dx, say, it's just going to be CD 1/2 rho Vx squared S ref. Yeah, and then S ref that's the reference surface area of your vehicle. So for Starship, for instance, the reference surface area, I basically said, okay, look, the thing is a circle. All right, so it's a 9-meter diameter, so it's got a 4.5-meter radius. Our area, of course, is going to be pi r squared is equal to the area. R squared, 4.5 squared is 20.25 times pi. You're looking at like about 60, right? 60 meters squared. Just for that. Then, what else is on Starship? Well, you got some fins. You got 4 grid fins. They're smaller than that. You got your 4 grid fins that eat up some area as well. Now keep in mind, the grid fins are not, it's not like they're just flaps sticking out there. They are aerodynamic surfaces. The part that's exposed to the wind isn't that much. Same thing with these flaps, not that much exposed to the wind. So what you'll see is basically, I did some calculations that I don't want to go into here, but I added another 25 meters squared there for those. So I ended up with about 85 meters squared for the SREF. That's going to be within, I think that's going to be within 20 or 30%. Shouldn't be hugely different from that, which isn't going to affect our numbers that much because drag losses really aren't that major, especially for a vehicle this large and heavy. CD. So there are two things we have to model here, right? SREF is a constant. We covered it. Now, keep in mind, if your vehicle is at some angle of attack, your SREF could change, where all this is now exposed to the slipstream. That's if you're at a larger angle of attack. However, like I talked about, we assume alpha equals 0, and as a result, SREF is constant. So SREF is constant. V is easy, just velocity, which we'll be able to calculate that easily. The two things we need to model are rho and CD. So coefficient of drag is definitely something we have to model, and you can look at it. So coefficient of drag is going to be a function of Mach number. Here's your Mach number. Here's your CD. Now, because a lot of weird things happen to the air at transonic speeds, which is about Mach 0.8 to 1.3, you have a huge spike in your coefficient of drag around Mach 1.3, and that really, your coefficient of drag stays inflated all the way through like Mach 4 or 5. So what you'll see is coefficient of drag around 0.2, and then topping out around 0.4, 0.42 or so, and we'll say this is Mach 1. This is Mach 5, and you can sort of extrapolate from there. The major irregularity happens around Mach 1, where your coefficient of drag goes from about 0.2 to 0.442 around Mach 1.3 or so, and then decreases sort of from there, and sort of is an exponential coming down to an asymptote, or not an asymptote, but probably near asymptote, as Mach increases to 10, 15, 20, 25, etc. And in reality anyway, by the time you get to these speeds, your atmospheric drag is so low that this doesn't matter anyway. But it is very important for this phase of flight, particularly around max Q, where your drag forces are the highest. And max Q does tend to happen around your CD max. We'll say, 1.3 Mach is your CD max. So what I did was I modeled the coefficient of drag. Now, I was able to use some basic data points of where Mach number was in relation to the drag coefficient. And from there, I was able to build a series of curves that explain the drag coefficient. Now, the issue here is that this curve, this drag curve, that you can see here, could not adequately be explained by just one curve. So I did have to make two curves. One for Mach is before 1.3, and one for Mach is after 1.3. So you'll see that prior to Mach 1.3, I use this curve, which is it's a second order polynomial, and you can see it just basically goes straight up, approaching approaching about 0.4, 0.42 at Mach 1.3, and you can see that reflected here. These are values that I basically hand jammed in order to get this equation, and then once I I fitted a line in Excel to these points. This is the best fit I could find. R squared of 0.8898, pretty good. Then I used the second order polynomial in order to calculate drag here. So you can see the CD below Mach 1.3 uses the second order polynomial related to Mach number. 0.4364 Mach squared, which is the same thing you'll see here, 0.4364 Mach squared, where x is your Mach number, as you can see along this this bottom axis right here. So that's the first segment. The second segment done almost the same way. This is after Mach 1.3. This is going to be a third order polynomial, which you can see right here, r squared 0.9943, pretty good. However, I found some major irregularities after Mach 1.8, after Mach 8, which is the furthest this graph goes. Now, that is always the danger in using these second, third order polynomials, right, is that once you get off the chart, you're in no man's land. There could be things happening off the chart that you have no idea about. So that's exactly what I saw. As I saw this this function went wildly negative after I don't remember, after Mach 10 or so, let's say. But so what I basically did as a result was after Mach 8.1, I just set the drag coefficient to a constant 0.15. Which is about where it asymptotes out anyway. And like I said, at that point, you're going more than Mach 8.1. You're far enough out of the atmosphere where drag isn't a major concern, at least for launch, right? Obviously, that's a totally different story for reentry, but that's a subject to be covered at another time. So, got this third order polynomial I used to model the coefficient of drag at a Mach number higher than 8.1, and you can, higher than 1.3, and you can see here I used a couple if statements in Excel to get that done. There's my third order polynomial, and then after 8.1 you have a constant CD of 1.5. So that's how we modeled CD. Now, the next thing we had to model was rho. Rho is your atmospheric density. Now, atmospheric density also varies. It varies much more, I guess, in a much more natural manner, as you'd expect, right, than Mach number, coefficient of drag does. Atmospheric pressure basically just decreases exponentially as a function of your altitude, as you'd expect. So I didn't have any good curves for that, so I did end up building one. I don't know which one of these I ended up using, but basically I took my atmospheric density. There are some data points available, for free online, data points of atmospheric or altitude versus atmospheric density. I built a couple of lines to fit that based on an equation, calculated a chi-squared value, which is basically just your the density minus what your equation said, your fit squared. And then from there I was able to run a solver optimization minimizing chi-squared and get an exponential function that minimized error, basically minimized this chi-square value. That's just using Excel's solver tool. I believe I performed that analysis with the help of a video on YouTube. I was able to use this method to make a exponential function that I could use to model atmospheric pressure, and you'll see I inserted that into the spreadsheet. It's the 2D trajectory modeling that you can see right here, and which I believe refers to these two cells. Yeah, so that's how I modeled atmospheric density. And you'll see, obviously, it decreases as you expect it to with altitude. The next, and I believe the last thing I had to model that was a pain in the butt was temperature. And you can see up here reflected the extreme measures I had to go to model temperature, which I don't recommend to anyone. Couple different sources for modeling temperature. One, obviously, the International Standard Atmosphere Wikipedia page. There's also a NASA page that does a decent job. If we go ahead and go to this Wikipedia page, I'll pull it up real quick. You can see basically different parts of the atmosphere have different base temperatures and different lapse rates. So I was able to use this to model the atmosphere. And basically, just using a series of if statements in Excel to model temperature. And the reason you do need a good temperature is Mach number varies greatly with temperature. Sorry, not Mach number. Well, it does because the speed of sound varies greatly with temperature. So you can see here the speed of sound is equal to 331 square root of 1 plus temperature over 273.15. That's Celsius, so I forgot what the relation is here. But basically, speed of sound varies 100% proportional to the square root of temperature. Temperature modeled as I discussed. Speed of sound just modeled, just a single equation based on temperature. Mach number, obviously, just your speed divided by the speed of sound. And then we get into the sum of x and sum of y forces. Sum of x, very simple, your thrust minus your drag. Sum of y, again, quite simple, thrust minus drag minus your weight. And then your weight, the only thing that's a little weird about your weight is that gravity actually does change with time, or sorry, specifically with altitude. So you'll see our gravity is dropping as we get further away from the Earth. And that's just because of Newton's universal law of gravitation. The distance further you are away from an object, the lower the gravity is. And that's covered in, I believe, my very first video, Intro to Launch Vehicles Part 1, as well as my orbits video. Last thing, x acceleration is just the sum of x forces divided by the mass. Y acceleration is the same thing. And you're going to be able to use those accelerations to get your x and y velocities here. It's velocity plus acceleration. Again, velocity plus acceleration. So, that's just your x naught plus vt, right? Where t here, we're doing every second, so there's no t. It's just x naught plus t. Again, for your downrange distance, you'll see it's x naught, which is this K12 value right here, which is your last distance, plus v. Normally it's v times t. Here t is 1 second. It's a 1 second interval, so t is 1 plus 1/2 at squared. Where t here again is 1, so you can neglect the t squared term. You just have 0.5 times a, which you see right there. It uses a from the last cell. So that's all there is to it. This is being modeled with basic high school physics formulas, or even, I don't know, middle school physics maybe. I don't know. Basic formulas and just integrated over time, and that's the beauty of being able to use Excel for something like that. I mean, get a nearly perfect solution because you're integrating this thing, over hundreds of samples. All right, so takeaways from this. Let's go ahead and look at a couple things. So initially velocity is 0, gamma is 90. Gamma 90 means we're pointed straight up. X and y velocities are 0, height 0, downrange distance 0, blah, blah, blah. Mass is higher. You'll see mass is going down as we fly. Gamma staying 90, and then going down here as we start to tip over. Our height is increasing, velocity is increasing in the y direction. As we tip over, velocity starts to increase in the x direction. Then vehicle weight steadily decreasing as we burn mass, as we burn fuel, right? Thrust is constant, thrust to weight ratio constantly going up. X and Y thrust varying with gamma only. Drag varying based on your coefficient of drag, as well as the atmospheric density. Then X and Y drag, coefficient of drag varying as discussed previously. Atmospheric density constantly going down as we increase in altitude, temperature varying, and speed of sound, Mach number, etc. Couple things to note. Let's see. First stage burnout. Velocity 1877 meters per second. Gamma 29 degrees. That means we're pointed 29 degrees above the horizon. At this point, at first stage burnout, our x velocity is already almost double our y velocity, so that's worth noting. Our height is going to be 71,000 meters. That's pretty realistic, pretty much what we expect. We're not quite in space, but we're quite high enough so that the atmosphere is almost negligible. 0.0004 kilograms per meter squared compared to 1.25, which is standard sea level. Vehicle mass 1811. So remember, that's going to be your entire fully fueled second stage plus your dry mass of your first stage and any residual propellant for your first stage. I think here we leave about 200 tons of propellant for the first stage to go do its boost back burn and its landing burn. Downrange distance, we're about 70 kilometers downrange when the first and second stage separate. Now, obviously, as the first stage, assuming, it's a recoverable first stage, if there were no boost back burn, the first stage would continue to would continue to travel downrange. Because they'll later be doing a boost back burn on the first stage, we would expect that downrange distance to start decreasing again on the first stage. Thrust is still constant. Thrust to weight ratio at burnout, 3.37, which is a reasonable value. So here you'll see we have 3 seconds of stage separation. Mass flow is 0. Thrust is 0. I'm saying basically they already separated from the get-go, so mass is lower. It doesn't affect anything too much. So as this goes, the vehicle is decreasing slightly in velocity, slightly in x velocity, and more considerably in y velocity because of gravity is pulling it down. All right, then second stage start at 188 seconds in flight, 0 seconds into second stage burn. Velocity, it's decreased from where it was, but it's going to start increasing again momentarily. Gamma, we're going to set 28 degree constant gamma. So basically, the vehicle is pointed 28 degrees above the horizon for the rest of the flight. And, our x velocity is going to be going up. Height will be initially going up. Eventually, it's going to start dropping. The other major takeaway from here is that thrust to weight ratio 0.79 initially, and as a result, our y acceleration is still negative 5.96 meters per second. So we're losing quite a lot of velocity in the y direction, and you'll notice that in the y direction, our velocity steadily decreasing through second stage burn, eventually becoming negative. So here we're actually losing altitude. Until finally we get going fast enough, maintaining our constant 28 degree gamma. We start gaining altitude again. Like I said, really ideally, a lofted trajectory would have 0 y velocity at the end of its burn, but I came pretty close. I'm not mad about it. All right, and then at the end of the second stage burn, here's what we got. Velocity, 7430 meters per second. Now, if you go back to our previous example, you'll see we need 7.81 kilometers per second, so 7,817 kilometers per second of velocity in the x direction in order to get in a circular orbit. Remember, though, that our launch site was already moving us at 408, so our actually V needed was 7409, and we've got 7422 in the x direction, so good to go. Height, 136,937 meters. Definitely in space at that point, not bad. Like I said, this doesn't account for the curvature of the Earth, so that might help you out a little more. you're you're in space at that point. There's a lot of drag down that low, so that is a concern. But definitely in space. So hey, congrats, we did it. We got 100 tons to orbit. Velocity is where we need it to be. Height is where we need it to be. We actually have some positive y velocity as well. So we're not at the periapsis. The apoapsis will be higher than 136,000 meters. So yeah, the vehicle can do it, no doubt about that. I'm assuming with some improvements in thrust and ISP, changing to 9 engines on the Starship itself, some stretch tanks. I expect they'll be able to improve on this considerably. I think a lot of the reason you see such a low number here is just because my model is not sufficiently accurate to really predict what the Starship can do. But you'll see it is accurate enough, at least, to say that, hey, it can do the thing. Let's see, anything else worth noting here. You'll notice thrust to weight ratio at burnout is 5.15, so quite high at burnout, even with 6 engines. So they're going to have to throttle, if they move to a 9-engine Starship, they're going to have to throttle down pretty considerably, I imagine, to avoid being extremely overpowered by second stage shutdown. And your Mach number at burnout, 27.12, ain't that nice? All right, so now that we've talked through pretty much this entire spreadsheet, let's look at some graphs, because this always sort of helps explain what's going on here. All right, so let's just go through these values one by one and see if we can explain what's going on. All right, first one, this is thrust. All right, it's constant, very high for the booster. When you switch to the ship, again, it's constant, still pretty high. All right, we'll get rid of that one. What is this? All right, this is Y thrust into the Y direction. Is that what we expect it to be? Let's see, so it's very high initially. It's going down as we decrease our gamma. And then over here, it becomes constant for the second stage. So is that right? Well, if you remember, we have a constant gamma for the second stage. So yes, our thrust is constant in that direction because we're not tilting the Starship at all. So yeah, that's exactly what we expect. Excellent. All right, next thing is going to be sum of x forces. All right, forces in the x are quite low starting out, as you'd expect, because we're both going slow and because the vehicle is pointed straight up. As we go over time, x forces are increasing because the vehicle is starting to point downrange and put more velocity downrange, and as a result, it's getting more drag downrange. That's for the first stage. Second stage, some of the x forces are constant. I'm assuming that's because drag is negligible, and again, we have a pretty constant. We have a constant thrust in the x direction. All right, what is this? X thrust. Yeah, basically the same. It just doesn't have drag, so that's explained the same way. This is going to be vehicle weight, steady decrease, smaller for the first stage, steady decrease, right? Smaller, steady decrease for the second stage. That's exactly what we expect. All right, this value is going to be our sum of y forces. Now this is interesting. So initially we've got high y forces. Y forces are increasing until about 90 seconds into flight. All right, so I looked at the the sum of y forces, and basically your thrust is staying about the same. You're tilting over a little, but it's negligible. Drag is getting higher all the way up until this 90-second mark, and actually your weight is getting lower as well. So that's going to the lower weight. It's being subtracted from your sum of y forces, so that's actually going to increase your y forces as well. So I think a combination of all those factors is causing the y forces to be more than double at 90 seconds what they were at the start. And then, as your vehicle continues to pitch over, you have a steady decrease in y forces, as you'd expect, as you pitch over more and more. For the second stage, you're going to have start with significant negative y forces because gravity is higher than your thrust in the y direction. However, as we move along, we see that the thrust in the y direction begins to outpace gravity, and sum of y forces become positive again. Downrange distance in meters. Yep, that's steadily increasing, just the way we'd expect it to, getting faster and faster as the vehicle gets faster. All right, these values are our y drag force and our total drag. Yep, increasing steadily until about that 90-second mark, and then decreasing steadily as we get out of the atmosphere. So, this happens about at CD max, which also happens to be a pretty dense part of the atmosphere, and then decreases steadily. And this is total drag, same thing there. Here we have our X drag force. Let's look at this one. So as opposed to Y drag force, X drag force is smaller. It peaks later. So I'm guessing it peaks later because, we're tilting over more and more. And, there just aren't as many X forces until we are tilting over more. Even though CD peaks over here, just the combination of I guess X velocity and CD don't peak until over here. So that makes sense to me. We'll get rid of that one. Height. Okay, so important takeaway here, right? We're increasing steadily in height. We loft the vehicle up to what is that, 150,000 meters, and then the vehicle starts to fall, and it's falling as we increase horizontal speed up to our orbital insertion speed. Like I said, ideally for a lofted trajectory, you would end at the sort of when you leveled out your altitude, but we end up going up a little bit. No big deal. This is mass flow in kilograms per second. Yep, that's exactly what we expect. High, and then lower with Starship, and starting out high with Super Heavy. Other things, vehicle mass in tons. Yep, starts out very high with Super Heavy, steady decrease. Starship is less. This is the dry mass. The difference between here and here is the dry mass of Super Heavy. After you get rid of that, then vehicle mass continues decreasing, albeit at a lower rate with Starship. These values are our X velocity. So you'll see X velocity steadily decreasing, momentarily dip momentary lapse right at second stage separation, and then steadily increasing again. That's our X velocity. I imagine this is total velocity. All right, this is going to be our downrange distance in kilometers, steadily increasing, no surprise. Our Y velocity in meters per second. Yep, so you can see it's steadily increasing until stage separation. At stage separation, it's steadily decreasing. However, as we continue to burn, our thrust-to-weight ratio improves. We slowly start to come back from that until we have a positive Y velocity at the end of our second stage burn. All right, this value is our gamma. Gamma is 90. Drops steadily with the gravity turn, and then is constant from there on out. X acceleration makes sense. Acceleration steadily increasing as mass decreases. Force remains constant. Acceleration goes up. That's what we expect. Mach number varies with temperature and speed of sound. Again, not concerned. Gravity slowly decreasing as we fly. So Y acceleration is interesting. It looks like it sort of has an inflection point here, and that's just where we're still turning to the side, that our greater velocity hasn't quite compensated for that yet. That's all that's happening there. And then here on the second stage, because we have a constant gamma, it exhibits more the behavior you would expect, where it's exponentially increasing your Y acceleration. This value is your angle of attack. You can see it starts off about 0 and then decreases very low, but toward the end of our flight, and starts coming back as we get the velocity vector closer to the gamma angle. But again, by the time it's so drastically far from 0, we are well out of the atmosphere, where it would be, or we're in a very thin part of the atmosphere where it's not a concern. All right, thrust-to-weight ratio increasing exponentially in both the first and second stage, as you would expect. Atmospheric density decreasing steadily and zeroing, as you would expect. Drag coefficient, again, exhibiting behavior you expect. You might not expect it to drop like this. That was just sort of a function of the way I modeled it. May not necessarily hold true, so that's something to look at next time. All right, that does it. So everything looked reasonable, right? Pretty much all the values we expected to see. So that leads me to believe that we've at least done a decent job of modeling this. All right, so that about does it. So just to sum everything up, we took some constants, some things that are publicly available information that we know about Starship, and we used those numbers to model the trajectory that we would need to insert ourselves into an orbit launching from Kennedy Space Center. And we were able to find that the vehicle could reach orbital velocity with an altitude of 137,000 meters, which is definitely in space, and still has some y velocity in the positive direction, so we expect its apoapsis would be slightly higher than that. And then, yeah, obviously, orbital velocity, you would need to add 408 meters per second to that, so actual orbital velocity, or actual velocity, you're looking at roughly, 7831 meters per second. So definitely at orbital speeds, and yeah, with 100 tons to orbit. So pretty exciting that no vehicle's been able to do that since the Saturn V. So will definitely be cool to see this first launch. All right, so yeah, that about does it. We talked a lot about Starship. We talked about some of the modeling we did. We went over a couple equations. We went over the publicly available information we have about Starship that we used for this video, and we talked about how we modeled Starship payload to orbit. Some things that we want to work on in the future are improving our accounting for the curvature of the Earth, and improving properly accounting for changes to the propulsion with altitude. And of course, we're going to have to modify the spreadsheet as new information comes out about future Raptors. Both, the Raptor 2 is going to have significant changes. We expect significant changes with future iterations of Starship and Super Heavy, specifically, upgrading Starship to a 9-engine vehicle. So we look forward to all that. Again, I apologize, the spreadsheet wasn't really as professional as I'd like it to be. Definitely still a work in progress, but I think it at least gives you a good idea of how you would start to address this problem. We covered a lot of useful things about rocket science and getting to orbit that honestly I'm super excited to share. So glad we got to do it. That's gonna do it for me. Thanks for watching Comprehensive Rocket Science. If you enjoyed, please like and subscribe, and yeah, we'll see you next time.